Hey guys, welcome to another video. Today we're starting a new topic in the Extension 1 syllabus, Perms and Combs, or Permutation combinations, or as they like to call it in the new syllabus, Combinatorics. So this topic was a frequent request in the comments section of the YouTube channel, so here it is. Hopefully it's helpful, especially for those that are about to hit the HSC next week on Extension 1. So if you like the video, please give it a like, subscribe to the channel, tell your friends. Let's start. So Perms and Combs is difficult. It's one of probably the top 3 difficult topics in Extension 1, up there with projectile motion and probably differential equation applications. So today the video isn't to sort of go through a lot of textbook easy questions, right? I will do one to start with, but thereafter, I want to explore some questions that are a bit more challenging and a bit more involved. So that's the context of the video. I'm proposing to do at least one video on perms, one on combinations, and see where that takes me. So today's video is only on permutations. Now, without going into much theory, let's just dive right into examples. For those that know, permutations, there's generally 2 types of questions. There's ones where the arrangements are done in a straight line, right? So for example, people queuing up for the cinema or arranging letters from a word, right? Mixing up letters in a word. What's important is if there's any, especially letters in a word, when there's any repeated letters or identical letters, right? Whatever number of factorials we do, we need to divide by the repeats, right? Same goes with any arrangements of identical things in a circle, but generally when we arrange things in a circle, we're dealing with people or unique items, so there's no repeats, generally speaking. So with that context in mind, hopefully you guys know your theory. Let's just dive right into it, do some past paper questions. Also, I've got 2 questions prepared at the end. Hopefully we get up to it, where for those that are unaware, Extension 2, about 3-4 years ago in the old syllabus, used to have permutations and combinations, right? That's now gone, being removed. But what so within the 4-unit syllabus, it used to be harder applications and harder techniques that are normally taught. They're gone now, and what your teachers, or what your 3-unit teachers are sort of doing, right? I can see it in past papers, is that they're throwing a lot of that 4-unit technique and questions into 3-unit. So let's cover a little bit. Just there's a really cool technique I want to show you today. If it's in your paper this year, or for those that are looking at this video for the future, if it's in your papers in the future, hopefully you get to apply the technique. All right, first question. Now this question, I say we're not doing a lot of textbook questions. This is a very textbook question. So let's just go there. In the word parramatta, how many arrangements are possible if there's no restrictions? R must be at either end and T's cannot be next to each other. I mean, that is very, very textbook, right? Very textbook, to the point where I'd actually say if this was in your past paper, it would be an easy, in this case, 6 marker. Wow, that's a lot. So what needs to be sort of identified firstly is what repeats are there. I can see there's 4 A's, right? And was it 2 R's and 2 T's, right? And 2 other letters. So maybe just identify that to yourself. There are 4 A's, 2 R's, and 2 T's, right? And 2 others, right, which is singular. So in this case, no restrictions would be quite simply, there are 10 letters all up. So 10 factorial, and then we deal with the repeats, right? Divide by 4 factorial, 2 factorial, 2 factorial, yeah? And once you punch it in calculator, hopefully the answer 37800. So let's go through that with a bit of pace, because I don't think that's particularly hard or particularly controversial. Let's go on. Part 2, the letter R has to be at either end, right? So I've got R and R there. Because there's 10 letters, there's 1, 2, 3, 4, 5, 6, 7, 8 other letters in the middle. Now, the way that I always teach my students to do it is deal with the arrangements as if they were non-repeated, and then deal with the repeats, adjust for the repeats after. I'll show you what I mean. So in this case, if the R's aren't repeated, and I've got 2 of them, right? To place the first R, there are 2 to choose from. Once I place that first R, place a second R, there's only 1 more. I've already used up the first one. And then within the middle, there are 8 factorial ways of arranging everybody else. So your answer at the end would be 2 times 1 times 8 factorial, right? Now that arrangement is assuming that there are no repeats. And then we just simply apply the repeat adjustment downstairs, right? To get my final answer to be, what's that, 840. Now, some teachers basically teach you by going, well, the R's, even if you arrange them separately, they don't matter because they're the same. Then essentially they basically remove the R's from the repeat. I mean, that's fine, but I think it's easier, well, at least the way that I teach it, for students to always retain the adjustment of 4 factorial 2, in this case, at the bottom for all questions. So you just calculate it as if there was no repeats and then adjust for the repeats thereafter. Hopefully that makes sense. Here, let's do number 3. T's cannot be next to each other now. To do this one, it's a simple case of considering the complementary event and removing it from the total, right? So we basically say T's not together should be equal to total, which is in this case, what do they call it? Unrestricted? No restrictions, right? Let's call that. So no restrictions less T's together, all right? Pretty straightforward. So I've already done that bit. That's 37800. And then T's together, like if you draw it diagrammatically, right? Put the 2 T's diagrammatically together and form a group with them, all right? Group them, where the other 8 letters can be 1, 2, 3, 4, 5, 6, 7, 8, can sort of move with it. And so what you sort of see, because the T's are together, they sort of act as a movable group. So call them, put a dot next to it and say that's a group. So if it's a group, then together with the other 8, there are 9 factorial ways of arranging that. And then within the group, right, forget about the repeats for now, we'll deal with that later. Within the group, the 2 T's can be arranged with 2 factorial in 2 factorial ways. So what that means is the answer for 2 T's together would be 9 factorial, 2 factorial, and then we deal with the repeats, right? That's the best way that I would teach my students to do this. Final answer being 30240. So guys, that question, not rocket science, right? Not the hard. In fact, if you got that in the test, easy 6 marks. Hopefully that's okay. Now, let's do one slightly more advanced, right? So that was Giraween. Now, Sydney boys, yeah, for those that have done past papers, I mean, you don't forget one like this. 5 Jovians and 4 Martians are sitting around discussing galactic peace, right? In how many ways? So 5J, 4Ms, right? In how many ways can be, that's unrestricted, right? Arrange in a table, so circle, right? So for the circle, the process is if there are 9 people, I'm going to lock one down, because if you don't lock one down, by moving the circle moving the arrangement in a circular manner, you're going to get repeats, right? So yeah, lock one down to avoid that. Now, the next bits are interesting. If Marvin the Martian will not sit next to any Jovians, right? He specifically does not want to sit next to the Jovians, right? And the next one, if all Jovians and all Martians sat together, so if all Jovians sat together and all Martians sat together and Marvin will still not sit next to it, okay. Let's go there. So for part 1. Part 1's easy. I've got 9 people or aliens in this case, A factorial, right? Lock one down, A factorial. What's that, guys? 40320, easy. Now number 2. This one's a little bit harder. So normally these questions, they basically go, oh, you know, there was a specific Martian that wanted to sit next to a specific Jovian, you know, and then they lead you into, they just, you know, in this question, step 2 or question 2 is immediately harder. Let's have a look. So draw yourself a circle. So it's good to identify Marvin the Martian, MA, right, and lock him down, right? So generally speaking, I say this to my students, if there is a person or specific object that they're talking about, that's the one you lock down in circle, right? Now, he will not sit next to Jovians. So you have all the Jovians on the other side, but what's more important is that it means that there is a Martian and a Martian on either side of his flank, right, on his sides. Now, it doesn't specify which a specific Martian, so it can be one of the other three, right, on each side. So what you do is you basically go, well, of the 3 Martians remaining, there are 3 choices to place on this side. And once I place one, there are 2 choices to place on this side. And there are 1, 2, 3, 4, 5, 6, of which 5 of them are Jovians and 1 Martian, 6 factorial for the other remaining ones. So in this case, the answer is 6 times 3 times 2, right? Which I believe would be 4320. Hope that's okay. Yeah, does that make sense? So place the 2 Martians on either side, right? 3 choices here, 2 choices there, 6 factorial for the remainder. Next one, slightly different in that, I mean, subtly different, right? It's subtly different, but you sort of have Marvin here as well. But what's important in this one is that all the Jovians, right, are on the other side in a group, right? Which leaves, now remember, Marvin does not want to sit next to Jovian, so there has to be at least one on each side, 1 Martian on each side. The other Martian cannot be part of the group now, so it's not 6 factorial, so it's slightly different. It's probably, it needs to sit within a group where the Martians are all in a group. Now, once again, lock Marvin down. So what that means is this, right? And this is really important. So the 3 other Martians, right, have 3 factorial ways of being arranged, right? And similarly, the Jovians have 5 factorial ways. Now, if you just did it like that, you're missing something, because if you think about the arrangement, this arrangement can be, so the way you sort of see it is, if Marvin was in a group and there were 4 Martians all up, then it's a bit asymmetrical in that there's one Martian on this side and 2 Martians on this side. But the different arrangement might be where there's 2 Martians on the left and 1 Martian on the right. So you have to allow for that, right? So basically within here, 2 factorial ways of arranging, right, the arrangement of 1 and 2, right? So you can have 2 on this side and 1 this side, and then it will be a different arrangement. So your final answer in this case will be 5 factorial times 3 factorial times 2 factorial. Let me just check that. Perfect. Yep. So type that in your calculator, 1440. Yeah. Hopefully that's okay. You know what? Let me just quickly check that as well on my calculator, just to make sure I am not making things up. 5 factorial, oops. 5 factorial times 3 factorial times 2 factorial. Perfect. Yeah, guys. So in this one, whenever you're dealing with cases where there's a specific person needing a certain requirement, I would always let that specific person as in a circle be the one that I lock down and then deal with the rest later. Is that okay? Now, because in the next question from James Ruse, you'll see that when there's no specific person, you have to create a specific person, right? You have to actually, create one yourself. So let's see. In how many ways can 4 men, 4 women be arranged in circle table? Okay. There is no easy question here, right? It's just 2. I think especially part 2, it's a little bit difficult, right? It's a little bit difficult, but let's say all women sit together and all men sit together, right? I think that let's start there. So for the first one, right, we've got 4 women, 4 men, all together in a group, right? All together in a group. Yeah, where when they're all in a group and there's nothing specific about anybody, right? There's nothing specific. You can lock a group down, right? So the women group stays on the top in this case, and the men group stays on the bottom. Now, if the men group is the only other group, then that's 1 factorial, right? It has to go there. I don't need to do anything more. And then your answer is quite simply, the 4 women have 4 factorial ways of arranging themselves in the group. The men, same. 4 factorial times 4 factorial is your answer, right? 4 factorial, 4 factorial. If you punch in your calculator, which I will as well. 576. Yeah, is that okay? That wasn't too hard, even though it was worth 2 marks. The next question worth 2 marks is much more intense. Let's see. All the men are in pairs separated by 2 pairs of women, right? So let's have a look. So if I had a circle, right? In this case, it's basically saying I have men, 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 women, 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 right? All separated by 2 pairs. So basically on the flanks, it's 2 pairs of women, right? If I were a pair of men. Now, given this arrangement, right? How do you deal with this? I need to lock someone down, right? I can't, this one here, the best way to do it is find a man, lock him down, because then inadvertently you've locked down the group as well, right? Inadvertently, you've locked down the group. So let's see. In this case, by the way, the groups can't move, right? The groups can't move. So you can, I mean, the men group has to stay there, and the women, I guess you can switch it, but the way you do the women is basically once you by locking down the men, this male here, and locking down this man group, right? The women groups have to be there. So, but because the groups of women aren't specified, it's almost like you just got 4 spots to fill, right? Just keep that in mind. So once you lock down the man in that group, right? The way I sort of see it is, let's see if this makes sense. Once you lock down that man, there are 1, 2, 3 men to arrange. So lock down a man in the group, so then there's no sort of circular motion, right? Circular arrangements possible. Lock down a man in that group. 3 factorial ways of arranging the 3 men, right? And then once you've done that, what you got to see is that actually, so for these 4 women groups, right? So 4 women in 2 groups, there are 4 ways to arrange the women. Yeah, 4 ways to arrange the women. But what's important, and maybe it's not as clear, right? 4 factorial ways. Because they're in groups, there actually is, once you place all the women, right, you can actually then switch them around, right, with 2 factorial ways. So the women groups can actually swap, right? So let me say it again. So in this case, we have a situation where actually, can I wind back, right? Can I wind back? The way I maybe should say this is, maybe the best way to say it, because actually, when I sort of said it out loud, I sort of disagreed with what I said earlier. When there are 4 spots left over, the 2 women groups actually don't matter. It's just a 4 factorial. What I should have said in the start was, don't lock down one specific man, lock down the group, right? Lock down the group. That's probably better. Yeah. And then within the first group, because you're choosing 1 man, right, to lock down within the group, you got to lock him down in one of the spots, right? There's 2 spots to lock down within this group. That one there's 2 factorial ways. Yeah. So once you choose within the group, the first group that you're dealing with, there are 2 factorial ways of locking down 1 man. Then you place the other 3 men wherever they lie. And then for the 4 women, there are 4 factorial ways of arranging them. So to do this question, to basically for me to explain it again, first step is to construct the 2 blues and the 2 pink groups. Once you develop the groups, it's a matter of placing the first individual man, because you want him locked down, right? But before you lock him down, he actually has 2 choices in his group to be placed. That's 2 factorial. 3 factorial represents the 3 other men that gets placed once you place down and lock down the 1 man, right? And once the men are taken care of, women, 4 factorial. So the final answer should be, and let me just check this, right, to make sure, yep, I'm not making up garbage. 432 factorial. If you punch in the calculator, let's check it out. 4, 3, 2, 288, is that right? Yeah, so check that, please. So for this one, hard, right? It's hard because you have to, in this case, lock someone down in a group. But before you lock him down in a group, he's got ways to move within that group of 2 factorial. So make sure once you do lock down that man, right, everything else sort of falls into place. 3 factorial for the other men, 4 factorial for the women, 288 in total. Guys, that was a few illustrations of technique on how to do circles. The first one on the line, I mean, it doesn't get much harder until next lesson when we start, from 10 letters, we choose 5. Right now, I want to do 2 quick questions to illustrate a 4-unit technique, right? A 4-unit technique. So in the HSC in 2012 in 4-unit, first question is easy. Second question, we'll see. All right, let's develop a method. In how many ways can M identical yellow discs and N black discs be arranged in a row, right? So maybe I will use the correct coloring. So I've got M yellow discs and N black discs, right? So it's saying I got M, I've got N. Right, how many can they be arranged in a row? Now, obviously then, together, that is M plus N, and they're identical, right? Perfect. So for part 1, it's as simple as M plus N factorial divided by the repeats. Yeah, cool. I don't think they need you to do it in like, just leave it like that. That's done. Now, part 2 is interesting, right? Part 2 is interesting. How many ways can 10 identical coins be placed into 4 identical boxes? 10 identical coins, 4 boxes. Now, I'm going to propose a method. So instead of doing this, right, some people start doing this, right? They start doing this. And they go, a few coins in here, a few coins in here, a few coins in here, and a few coins in here, right? I mean, that's fine. That'll take you forever because I've seen students try to do this by using cases. They go, case number 1, when the first box has everything. Case number 2, when the second or first 2 boxes have stuff. Third one, it gets all complicated. The theory that gets applied that works really well, right? That I'm not sure whether it's still taught is, instead of considering 4 boxes, because if you look at where the arrangements are, right? You got some on here, some in here, some in here, some in here. What you've essentially done is arrange things with a gap between them. I'm going to call this gap a divider, right? You've basically, for 4 separate compartments, you've basically introduced 3 identical, right? Separators or dividers. So in this case, right? In this case, what I want you to see is that if you introduce 3 identical dividers, you're arranging now in total 13 items, right? Of which 10 of them are identical coins. So you can go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or in any other combinations. So you basically arrange the blue and you arrange the yellow. So your answer is actually, you're arranging 13 items divided by 10 coins, which are identical, and 3 items, which are identical dividers. That's the answer, right? So when people looked at this question and saw the HSC solutions and they saw 13, they're like, where did that come from? The theory that they teach you in 4-unit is that they introduce this concept of an identical divider. It's a really cool way to attack questions that have compartments, right? Now, I'm going to show you one more question where this theory comes to the fore. However, it looks like when they taught the question, they didn't teach this method. And I'll show you how the answers deal with it. I'll actually copy and paste the answer for you just to show you the complication of why it's worth 3 marks. So this last question I want to cover today from the CSSA in 2010, 5 identical rings are placed on 4 fingers, right? Not the thumb, 4 fingers. So you have, diagrammatically now, excuse my, that's a thumb. But I have 1, 2, 3, 4, right? 4 fingers, so ignore the thumb, all right? Ignore the thumb. I got 5 rings. So I got 1 ring, 2, 3, 4, and maybe a 5th one over here, right? 5 rings. And how many ways can this be done for 3 marks? Now, if you were to approach this using a case method, right? Let me cut and paste, watch the complex. This is the answer, right? Wow. This was a solution from the CSSA. They basically go, is considered, what if all the rings were in 1 finger, right? What if 4 rings were on 1? Look at it, guys. That's why they gave it 3 marks. But if you were cool enough to apply the divider method, right? This is basically 4 compartments in 3 with 3 identical dividers. To attack this question, actually, you know what? I'm just going to leave this calculation up here, right? Just so I can compare it, right? So instead of doing this way, you can go, or you go, I've got 5 things to place, right? Including the dividers, there are now 8 items, of which 3 of them, right? 3 identical dividers. So then the answer would be 8 factorial ways, because I can arrange the dividers as well, right? All over 5 rings, which are identical, and 3 identical dividers. Now, I'm hoping, guys, let's punch this in the calculator, that if I do, the answer is 56. 8 factorial, 5 factorial times 3 factorial. Look at that. 56 ways, 56 ways. So you can do this if you wanted to, or appreciate the divider method. Guys, hopefully that was okay. If you like that, subscribe to the channel, please. If you haven't done so, like the video, tell your friends, right? HSC for this for extension 1 is next week. Hopefully this is useful. Guys, the next lesson is combinatorics. I want to once again explore some easy questions to start the video off, but then of course, let's hit up some more challenging questions. See you guys later.